Greetings, fellow knowledge seekers and cosmic wanderers. I'm Ernis, your guide for today's exploration. Ever feel like you're staring into a dark nebula, trying to find a single, solitary star? That's often how it feels when we're facing complex problems, isn't it? Well, today, we're going to turn on the cosmic spotlight and explore a fascinating paper that does just that for skin cancer diagnosis. We are delving towards explainable skin cancer classification, a dual network attention model with lesion segmentation and clinical metadata fusion. Now, that sounds like a mouthful, I know, but don't worry, we'll break this down like Richard Feynman explaining quantum physics to a room full of kindergartners. Now, why should you care about skin cancer classification? Think of it this way: early detection is the difference between a tiny spark and a raging wildfire. This paper tackles the problem of improving the accuracy and, crucially, the interpretability of AI models used to diagnose skin cancer from those magnified dermoscopic images. So, imagine a cosmic library, where each book holds a piece of the puzzle. Let's organize our journey through this paper into 3 distinct sections, each a room in our mental memory palace. First, we have lesion segmentation. Picture this as the foundation of our AI diagnostician's house. It's all about isolating the suspicious area from the surrounding skin. The authors here built a special deep UNET architecture. Think of as the classic blueprint, but they added dual attention gates and something called spatial pyramid pooling. These are like adding extra sensitive sensors and zoom lenses to the system, making sure it doesn't miss any important details, regardless of the lesion's size or shape. They're essentially teaching the computer to really see the thing it needs to analyze. Second, we step into the dual encoder classification chamber. This is where things get really interesting. Imagine 2 detectives looking at the same crime scene but from different angles. One detective looks at the overall scene, while the other zooms in on the key evidence. That's exactly what's happening here. The researchers used 2 dense net 201 encoders. One looks at the original image, and the other focuses on the segmented lesion. Now, to make sure those detectives are sharing information, they use something called a multi-head cross-attention module. Picture this as a super efficient communication system that allows the 2 encoders to highlight the most relevant information from each other. So the encoder looking at the big picture can say, "Hey, zoom in, guy, pay extra attention to this particular area," and vice versa. And finally, we arrive at the clinical metadata integration room. This is where the AI gets a bit more human-like. It's not just looking at images, it's also considering patient information like age, sex, and the location of the lesion. The authors use a transformer-based module to incorporate this data. Think of it as the AI interviewing the patient and adding that context to its analysis. It's like saying, okay, I see this lesion, but I also know this patient is a 60-year-old male, which changes the probabilities a bit. Now, you might be thinking, okay, Ernie, that sounds complex. How do we know this thing actually works and isn't just some fancy algorithm spitting out random guesses? Well, that's where the explainability part comes in. The authors use a technique called gradient-weighted class activation mapping, or GRA. Think of GRA as a heat map that highlights the areas of the image that the AI is paying the most attention to. By visualizing these heat maps, the researchers could confirm that their model was indeed focusing on the lesion itself, not some random artifact or irrelevant background feature. It's like showing your work in math class. To test this design, the team ran their model on a few major datasets like the HAM1 and ISIC challenges. Here's where things get concrete. The model didn't just perform slightly better. It blew past existing models in both accuracy and something called average AUC. Think of that as a measure of how well the model distinguishes between different classes of skin lesions. And, critically, the GRA visualizations confirmed that the model's predictions were based on actual lesion characteristics, not spurious background noise. Now, there's a dash of Rick Sanchez-style skepticism we need to address. I can already hear some of you saying, fine, yeah, another AI model. So what? Will it actually help doctors? This is where the potential real-world impact shines through. By creating a more accurate and Interpretable model, this research could lead to tools that help dermatologists make faster, more confident diagnoses. Imagine a future where AI assists doctors in identifying skin cancer early, saving lives and reducing the need for unnecessary biopsies. So, what's the big takeaway from this cosmic voyage? This paper demonstrates that by combining precise lesion segmentation, dual encoder attention, and clinical metadata, we can create AI models that are not only highly accurate but also transparent and trustworthy. That's a huge step towards building AI systems that can truly augment and enhance human expertise in the fight against skin cancer. And that's it for today's journey into the world of skin cancer classification. I hope you found this exploration as enlightening and inspiring as I did. Until next time, keep exploring, keep questioning, and keep seeking knowledge.